So let's go on to our next story, which is another discovery with TESS that was announced for the star GJ357. And this is another three-star or three-planet system. And so here again is the light curve from the TESS satellite. And those red points show you where the planet transits, where the planet blocked the starlight. And you can see how the star itself is varying because these M dwarfs, these low mass red stars, have star spots. They have variability in how bright they are intrinsically. And so there is this sort of intrinsic variation, but then you have these dips due to the transiting effect. And so here they've combined all the transit data. So again, you can see these nice little drops, again, on the order of 0.1%. So very small change in the brightness of the star. And the other thing that they did was to combine the TESS data, which is the transit data where you're blocking the starlight, with ground observations from about half a dozen different observatories where they're also getting the radial velocity data, so getting that reflex motion of the star. And again, you get these sinusoidal curves, and it's pretty noisy because you're looking from the ground. And look at the speed of the star. It's on the order of about 2 meters per second. So this is basically the walking, if you were to walk, that's how fast you would be moving, a fast clip. And that's how sensitive these instruments are to the motions of these stars. We can basically detect them at walking speeds. And here is what that system looks like. These are artist depictions of those three worlds. And what's interesting is that the inner two worlds, GJ357b and C, are much too hot, but 357d lies in the star's habitable zone, meaning if they're, and actually it turns out that this world, if it had a really thick atmosphere full of carbon dioxide, the surface temperatures would be temperate enough to allow for liquid water to exist. So whether water exists or not, we don't really know. We'd have to wait for follow-up observations with future telescopes, but this is another really intriguing result. Now, unfortunately, what astronomers have also realized in recent years is that even though M dwarfs are very common in our galaxy, and all the stars that we've seen so far are these M dwarfs, these low-mass red stars. M dwarfs can also be very active, meaning they can send out these flares of radiation. So we know our sun periodically sends out flares, but these M dwarf star flares can be much more powerful than the ones that we observe from our sun. And so the amount of ultraviolet radiation from these stars could potentially be catastrophic for life, meaning if you had flaring from these stars and you had a planet that had oceans or life on them, that the huge amount of UV radiation could potentially disrupt the life or even wipe it out. And in fact, just a couple years ago, astronomers detected flaring from Proxima Centauri, which is the closest star to us. And we know there is a planet there. And one of the results of this paper that came out is that the size of the flaring, and if it is very common to M stars, then it could wreak havoc on any biospheres that might exist. And it could even prevent life from starting or destroy life once it started going on that planet. But and so here is just a graphic showing that the flare resulted in a brightness from that star that was 1,000 times greater than normal, and that tells you how much energy is in those flares. But despite that, at least here on Earth, we know that organisms have developed ways to protect themselves from ultraviolet radiation. So one of the things that you can do is you can be under an ocean of water. The water can help protect you from UV flares. You could also be buried underneath in the ground. that, being underground would obviously protect you as well, but being underwater or being underground would make it more difficult for you to detect any life like that. But some authors have come up with a really innovative and kind of ingenious idea about protection from flares, and also having something that would make it observable from astronomers on Earth, and that is fluorescence. And here on Earth, organisms' life has evolved fluorescence multiple times. So we see it in plants, we see it in animals, different types of animals. So what fluorescence basically is it's an adaptation where proteins or other molecules on plants or animals absorb UV radiation, and then they re-emit it at optical wavelengths. And so you can shine UV lights on animals like jellyfish, or lobsters, or frogs, or butterflies, or different types of fish. And in all those cases, they absorb the UV. They've evolved this protective mechanism to absorb harmful UV and then re-emit it in blues or greens or reds. And so these authors wondered whether in another organism that fluoresces are corals. And what's nice about corals is that corals are an organism that can grow in these giant coral reefs. And so if you imagine an alien coral system that covers a significant fraction of the planet, these authors wondered, could you see or observe corals fluorescing on an exoplanet? And what they did was to create computer models of flaring stars. And so this is a plot showing what the spectrum of the sun is at UV wavelengths. And this is what one of these M stars, how it would look in the ultraviolet when it's not flaring. But when it's flaring, this is the spectrum. This is the light that's emitted at different wavelengths. And so these M dwarfs, even though they're less luminous and not as bright as our sun, when they flare, their UV light can be much greater than the light, the equivalent UV from the sun. And so they input in these different models for the spectra of different types of M dwarf stars. This is the solar spectrum, again, by comparison. So normally they are emitting at far redder wavelengths towards into the infrared, and the ultraviolet is down here. But so normally they normally don't have very much ultraviolet, but then when they start flaring, the ultraviolet increases by quite a bit. And these are some of the results. And so this is kind of a complicated plot, but what we're seeing here is basically what the spectrum of vegetation will look like. So this hump is kind of in the red. So if you assume that if alien vegetation looked like ours, this is how it would reflect. And then they looked at different corals that were fluorescing either in the green or in the blue, and you can see that the amount of fluorescence is quite a lot brighter than the light coming from the visible wavelengths. And these different rows represent different amounts of oceans. So a fraction of ocean cover on the planet. This top row represents the entire planet covered by fluorescent corals. Here you have either 50% or 70% ocean. So that's what these different lines represent. And then this bottom row represents different amounts of cloud cover, which changes what you can see. And then they finally point out that for red dwarfs that we know to have planets around, and we can even look at we observe how distant they are or what separation they have between the planet and the parent star. And this measure is in milli-arcseconds, or 1,000th of an arcsecond. And so this is an extremely tiny measure, and it turns out that next generation ground-based telescopes, there are telescopes on the drawing boards right now that have mirrors about 100 feet across. And with those telescopes, you can potentially resolve objects that are only separated by about 6 milli-arcseconds. So that tells us that if these worlds that are this far separated from their parent stars do have these fluorescent coral-like colonies, and that's a big if, then these future telescopes could potentially detect the biosignatures of this alien life. All right, those are my stories, and I'm going to hand it off to Steve.